In the temperature diagrams, it flips. So keep track of that. In the temperature versus mole fraction diagrams, now look, the vapor is on top and the temperature is on the bottom, okay? So suppose that I want to go do this. So let's draw like my nice little still. So maybe here's my round bottom flask. Here's my fractionating column, you know, with my thermometer in there somewhere. Maybe I'm using an electronic thermocouple right there, okay? And then here is my sidearm right there, right, that I know I'm adding cold water in to make condensation. And then now here on the other side, it drips out into my little collection flask. This is a pretty terrible looking still, okay, for distilling, let's say, some liquid. So how does this work on my temperature mole fraction diagram, okay? Well, suppose I start at A1. So start at A1, okay? And A1 is not boiling yet, so that's why it's down here. It's not quite on this line, because what this line represents now, this blue line, gives me my boiling temperature of the liquid at any one of these compositions. And as you can see, when the mole fraction of A is pure, you can see that there's a lowering of the boiling point by adding more stuff, so that makes sense, okay? And so now what I do, I've got my liquid in here, and I heat it up to the point where it starts boiling, okay? So now that takes us all the way up to this composition A2, okay? So now my mixture is boiling at A2. The mole fraction of A is still the same in the liquid, but look, the vapor will be more enriched in A. So as this is now condensing, as my liquid comes over and condenses, this will be the vapor composition of the condensate. Oh, excuse me. And so now what happens in this thing, when it goes into this sidearm where there's cooling water, right, it's going to cool it down. Okay, so follow this diagram, right? It goes up, it boils at A2. The vapor composition is A2 prime, so it's more enriched in A. And now as it cools down, when it enters this side flask here, it's going to cool down to this composition A3 in my little still, right, in my flask. And we note here that now A, right, the mole fraction of A in the solution has increased. And if we were to keep doing this, so here what I've actually just described is a regular old still, but if we had a fractional distillation, so in other words, you put all these little like glass beads in here, okay? All those little glass beads are cold. So actually what happens, this process I described where it boils and then A is more enriched and then it cools again, this is actually going on in the fractionating column before it even comes over, okay? And so what happens then in this fractionating column, you're getting a lot of this boiling and cooling and boiling and cooling and boiling and cooling. And every time that happens on this diagram, you go up, you go over, and then you go down. And then you now are boiling it again. And so now A is even more enriched. It cools down to this liquid composition, and it just keeps going. And as you might imagine, you just keep going until you have pure A. So this is how you could actually separate something by boiling in this fractional distillation, okay? Well, as it turns out, there's two particular types here, or excuse me, let me back up for just a second. So in this diagram, this is showing us a totally ideal solution, one that would allow us to completely separate A from B. So in this fractionating column, so all these steps are going on here. And so now eventually when you have just pure A, when it makes it out of the top, there will only be A in that side, and of course there's A and B in this side, okay?